Refraction describes the process of waves going from one medium to another. What happens to the light when it changes media? Refraction is responsible for the fact that Shoshana appears to have two faces, one here, outside the glass, and a completely different one several inches away, inside the glass. Refraction, when taken to extremes, can even manage to switch things and make them appear precisely where they are not. Refraction can be seen as hot air shimmers above a cooler surface. Things get magnified beyond all proportions. They get mirrored and make mirages where they are not there at all. They switch directions, flip upside down, and even split into different colors. What do waves do when one medium ends and another begins? Do they speed up, slow down, stop, turn? Consider the conga dancing example that we did in class. When all of a sudden the person in the front has to slow way down, what happens to the rest of the line? What happens to their speed? What happens to their direction? Can two people run together at different speeds? Consider a three-legged race. Sooner or later, if they're running at different speeds, one of them isn't going to be able to keep up with the other. That means the one who's running faster is going to be pulled back and slowed down. Where? Where they're joined. Waves work the same way. If the waves encounter a new medium and one of them has to slow down, the other one will get pulled back and bent like this. As you saw in class with the conga dancers, slowing down is going to shorten the wavelength and is going to bend the whole line, the same way the path bends when one sine is traveling slower than the other. When you look at something submerged in different media, here we have air, glass, oil, and water, you can see very dramatically the bending of the light. It's not that the pencil's bent, it's not that the pencil's bigger in the oil and the water than it is in the glass, and bigger in the glass than it is in the air. It's that the light is being bent. Refraction is the bending of the light when it slows down or speeds up from one medium to another. Check. Does refraction depend on density? Look at the picture and make sure. Check again. What's more dense, the water on the bottom and the oil on the top? Now, where do you see the most dramatic bend and the most dramatic magnification? In the oil, which is less dense, or in the water, which is more dense? Well, it was worth a try. Refraction does not depend on density. It would make sense that light would slow down in denser media, and sometimes it does, but just as often it doesn't. Oil and water, case in point. Refraction is a property all its own. Check out refraction in 2 dimensions. That's pretty cool, isn't it? 2 coffee cups? Nah, 2 light rays. If you're looking from one media on one side at one angle, one light ray will bend one way. But if you're looking at the same object in the same medium through a different angle, you'll have another light ray bending the other way. 2 rays bending in 2 different directions will reach your eye, and you will see 2 different objects. Refraction, we've said, is how much light speeds up or slows down. How does that relate to how light bends, and what does it depend on if it doesn't depend on density? The index of refraction is an index on a scale of, well, we'll specify the scale in a minute, it's not 1 to 10, of how much the light is going to bend. N, the index of refraction, is the speed of light in a vacuum divided by the speed in a new medium. Yeah, I know it should be I for index, but I was already used both for current and for rotational inertia, so N, at least it's not Q. Take the speed of light in a vacuum, now take the speed in a new medium. Take the ratio, and you'll see how much light is going to... Wait a minute, if it's coming from a vacuum, it's only going to do one thing, and that's going to slow down. You never take the speed of light in the vacuum and speed it up. That means the speed in the medium is going to be what? Compare the denominator to the numerator. Decide which is always bigger, and write down an important fact about n. How big can n get? How small can n get? Think about it for a minute, pause the video, write it down, then play to check your work. Look, it's always going to slow down in a new medium, and it's never going to speed up. N is always going to be a number that's greater than 1. If n equals 1, the speed in the new medium would be the same as the speed in a vacuum. That would mean that the new medium is a vacuum, which it isn't. How do we find the index of refraction? Measure it in a lab. How much does light slow down in air? Well, it slows down by 0.029%. To 3 sig figs, light travels as fast in air as it does in a vacuum, and that's why light looks normal and looks like it's traveling in straight lines when it's streaming through the air. Water, on the other hand, slows light down by 33%, and we can see things definitely looking bent and warped when we're seeing them underwater. Oil, as we saw, slows light down more than water, which is why we got more dramatic optical effects when the pencil was submerged in the oil. Plastic is on the same scale as oil. Every different kind of plastic has a different index of refraction. Lucite plastic slows light down by 49%. You'll measure the index of refraction for acrylic plastic in the lab. Crown glass slows light down by 52%. Flint glass by 64%. Different types of glass, different indices of refraction. Crown glass is used for watches and dials. Flint glass is the kind that's used in chemistry test tubes. By the time we get to lead crystal, the speed of light has been fully cut in half. Index of refraction, 2.0. Cubic zirconium, synthetic diamond, is the highest index of refraction that humans can make in a laboratory, slowing light down by 2.21. That is cutting the speed of light more than in half. The largest index of refraction known to humankind is real diamond, and that's an index of refraction of 2.42. Take a look at all these materials on the list, going from various liquids to plastic, to glass, to crystal, think Swarovski, to synthetic jewels, to real jewels. Look what's happening as we go up and up on the index of refraction. What do you notice about the materials? It's not necessarily that they're getting more solid, because we can get oils and plastics that have the same indices of refraction. What do you notice as index of refraction goes up about the quality of the material? Plastic, glass, crystal, synthetic jewels, real jewels. What quantity does index of refraction confer? Or perhaps we should say, what quality does index of refraction confer? Think about it. We're going to apply it by the end of the lab.
Come listen and learn, I've a story to tell. I sing of the genius of Philip Snell, a mathematician who lived long ago in the Netherlands where the Rhine River does flow. He set for his mind occupations of worth, improved navigation and measured the earth. He gave us the sine law, that wonderful guy, and he made more precise calculation of pi. Singing in 1 sine theta sub 1 hey 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 equals n2 sine theta sub 2 hip hooray. His greatest feat came in 1621, when optics as science was really begun. While flashes of lightning illumined his page, he wrote down Snell's law, his great gift to the age. So if you wear glasses or like to fry ants, be grateful your lenses were not made by chance. Astronomers hail him with each newfound star, microscopists toast him from each sleazy bar. Singing in 1 sine theta sub 1 hey 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 equals n2 sine theta sub 2 hip hooray.
The Ballad of Snell's Law by Russ and Eli.
Others take heart, both studied refraction, and both were real smart. But we prefer Villefort, Van Roy, and Snell. He laid down the law and he did it darn well. Singing in 1 sine theta sub 1 hey hey hey
Equals n2 sine theta sub 2
hip hooray.
Snell's law gives us the relationship between the index of refraction and how much light bends, the idea that we've been working on from the start. Snell noticed what you guys noticed about the wave spacing. The wavelength gets shortened only in one dimension, forward and backward. When you did your conga dance, you all crashed into each other forward and backward, but your horizontal spacing didn't change. That's one component, that's the vertical component, that's the sine. Snell tried it, and it worked, and he formalized the sine law. Snell knew not to measure angles from the surface of the glass or the water or whatever it was he was working with. For one thing, if you have waves, the surface of the water is going to be really hard to put a protractor on, and your protractor will get very wet. Snell's law is measured from the normal, a line drawn perpendicular to the surface. It's absolutely flat and straight and perfect. Why? Because you drew it with a ruler and you took responsibility for it yourself. Theta 1, the angle of incidence, is the angle it made in the first medium, the one that it was leaving. In this case, the air. Theta 2, the angle of refraction, is the angle it made, again, with the normal in the new medium, such as the water. Which is the bigger angle? Let's find out. Let's take Snell's law from air into water. It's going to look something like this. We're underwater, looking out at something that's in the air. In order for us to see, the light has to come from the air above into the water below. Our angle of incidence is 45 degrees. N1 is the N for the air. What is it? Look it up. What's theta 2? At what angle will light come into the water where we, underwater, can see it? Look up N2 for water, set up Snell's law, and solve. Don't forget to use your inverse trig functions because you can't divide by a sign. Pause the video and unpause when you've got an answer. Check. Where do you measure from? You're measuring from the normal. Make sure your picture is accurate. Make sure your equation is accurate. As you find theta 2, take a look at your answer. Which angle is bigger? If you got an angle of refraction that is significantly smaller, is the light bending in and getting smaller, or getting out, bending out and getting bigger? Is your answer of 37.2 degrees going to make the image look smaller and shrunken compared to its original 45, or magnified, bigger? Look at that photo again. Better still, look at this one. These scuba divers appear to have gone to a head shrinker. Look, the parts of their head that are over the water appear significantly smaller than the rest of their bodies that are here with us under the water. When light goes from air to water, the result looks much smaller than it ought to, creating some really neat optical illusions. Now try the related problem, light streaming from water, where the swimmer is, into air. Can you see the light bending already on its way out from the water into our eyes? This time, the angle of incidence, theta 1, is underwater. Check the index of refraction. And the new angle, the one it's streaming to, is in the air. That's going to be theta 2. Check the index of refraction for that as well. Pause the video, unpause when you're ready to evaluate your answer when you found theta 2, the angle of refraction. At what angle will the light come out into the air and be visible? Now, is your new angle bigger than your old one, like 70 degrees bigger? If so, has the light bent in towards the normal or bent out away from the normal? Will it make what's underwater appear magnified, bigger, or smaller? Think about it. As far as we're concerned, objects underwater are not where they appear to be. The light looks like it's coming to your eyes in a straight line path, but it's not. It's bending. Objects encased in glass are also not the size and shape they appear to be. Check it out. Thick glass or plastic pint mug appears to contain more root beer or equivalent pint beverage than it really does. The light rays bending outward magnify the image that we see. Put the mug underwater, where the difference in index of refraction is much less dramatic, and you'll see what you're really paying for when you buy that drink. That mug is not as full as it looks.